All right. We will have lab today, of course. You know that. Basically, what we're doing is measurements and looking at different ways we can measure objects and how it affects density, okay, and how we calculate density. All right. If you remember from last week, we were discussing free fall. We've already talked about free fall. I'll pause that a minute. And one of the things we said about free fall, of course, is an object in free fall, regardless of its mass, it has what? It will fall what? Regardless of an object's mass. If I take two objects, let's say I take this marker and this steel ball, they do what? They hit at the same time, don't they? Every time, okay? We know that ball's a lot more massive than this marker, okay? So we know that gravity is what? Gravity is constant. Now, of course, you've always got to remember that's with respect to where you are. Understand that gravity at Denver, Colorado, and gravity down here at Gulf Shores on the shoreline, it's going to be a little bit different. But for Denver, it's constant. For Gulf Shores, it's constant, whatever the value is. Because remember, you're farther away from the center of the Earth. You go into orbit, you're in free fall. Okay, you're in what's called microgravity. There's very, very, very little gravitational acceleration, okay, because you're so far away from the center of the Earth. Okay, all right, so I don't know if any of you ever seen this demo. Anybody ever seen this shoot the monkey demo? Your high school teachers had ever shown you this? Okay, it's MIT. MIT, they have some, their professors, I don't know, you may get online and want to watch and see what they say about something we cover, and that's fine, I don't care, because sometimes I watch what other people say too, because sometimes I pick up on something, hey, I need to present it that way instead of the way I'm doing it, because it makes more sense. So they have a lot of good videos out there. Khan Academy has really good videos, okay? They're really good videos. That guy's really good at explaining things simply in a simple format. Okay, so let's look at the monkey and the gun. All right, now, what they're going to do is you're going to see here, they're going to come in here and they're going to load this projectile launcher, and we will probably do that lab a little later on, maybe next week or week after, I'm not sure. But I always try to do that lab. The only thing with it is we tear the room apart, but nah, whatever, you can put it back, okay? So notice he's going to aim this projectile launcher at this monkey. Now there's other videos out there too. One video they use a human with a baseball glove, and that's pretty neat. I think it's at the University of Minnesota. Now what he's doing is he's aiming the projectile launcher right at the center of the monkey's chest, okay? Now that's key, all right? He's aiming it at the monkey, okay? So what do you think is going to happen? Will the ball that he's fixed to fire out of that projectile hit the monkey if they're released simultaneously? He's aiming it right at it, right? Okay. Okay, so 2 or 3 of you said yes. Some of you are not sure. Well, let's see what happens. Okay. I love this demo. Video's a little dated, but that's okay. Notice they still use chalkboard. Oh, what was that? All right, they'll play it again. Slow motion. Boom, right in the center of the chest. Isn't that crazy? How does that work? Well, regardless of mass, objects fall at the same rate, same acceleration. And they hit the poor little monkey and he squeals like crazy because they hit him in the chest. All right. So, and there's another demo we could watch, but we're not going to do that, okay? Well, some of the things that pop up, oh well, anyway. Moving along. All right, I'm not ready for that yet. Let me pause my video, okay? Okay. Anytime something is, come on now. Anytime something is uniform, that means it's what? Something is constant, isn't it? You have something that is constant in the motion, right? So what is going to be constant in our motion? Well, notice that right there. What's going to be constant? So velocity's constant, isn't it? Okay. Well, Mr. Shields, I thought you said now we're talking about centripetal acceleration here in a minute. If something's constant, if velocity's constant, we don't have acceleration. Well, is that true? Well, it all depends on how it's moving. All right? Because you know as well as I do, I just told you, and you've probably done it with when you was a kid, take a rope and a bucket and put water in it and swing it, okay? If you shorten the radius of that rope, boy, you really got to hold on to it, don't you? But if, you've got it out there a couple of feet, you don't have to hold on quite as hard. Okay, well, why? Because the radius is changing, the time interval's changing. Okay, as the radius gets shorter and the time interval gets shorter, guess what? The acceleration increases. Okay, inversely proportional to each other. All right, so even though velocity is constant, we still have acceleration. Now, this is a little bit hard for some people to wrap their brain around, but why do we still have acceleration? So even though you have uniform circular motion and the velocity is constant, you still have acceleration. Okay, it still accelerates, okay? You still have acceleration. Why? Why do we still have acceleration? All right, well, if I had let that string go, let's say if I had taken it and I'm spinning it, okay? And I really like doing it better with a string than a car, because typically cars don't go in circles, do they? Unless you're on a racetrack, okay? All right, so if I'm spinning this and I let the string go as the ball gets right here, I'll let it go just as the pendulum gets right here. Where's the ball going to go? Is it going to go up? Is it going to go down? Is it going to go straight this way? Okay. Okay. So if I release it here, is it going to do this, or is it going to go? And I know it's a little hard to do, but remember now, think about your velocity vector. Okay. And think about where acceleration is. So is the ball going to go this way, or is it going to go that way? What if the ball, let's see, now it's moving this way, isn't it? So it's coming up, so which way is the ball going to go? Is it going to go that way, or is it going to go up? It's going to go up. Well, how do you know that? Well, which way is it moving at this point? It's pointing straight up. What if it was right here? Which way is it going to go? I think this is what some of you were thinking. It's going to go that way, isn't it? If I let it go right here, it's going to go that way, right? And of course, if I let it go right here, which way is it going to go? Straight down. Okay? And you say, how can that be? Well, because of the direction of your velocity vector. Okay? Okay. So the velocity vector at this point in time for the car, just like with the ball, if you were to break the string right here, break it, then the ball, let's just pretend that's the pendulum bob, okay? It's going to go in that direction of the velocity vector, okay? All right. Okay, so the speed, even though it's constant, how do we have acceleration? Well, let me ask you something. If you take the ball here and then you put it here in its path, notice the direction. Now where's the direction of my velocity vector? Is it still pointed that way, or is it pointed this way? You follow me? If we come on around here, where's the direction of my velocity vector? That way, isn't it? So what is changing as this car or a ball on a string goes in a circle? The velocity is not changing if it's uniform, but what is changing? Direction. Very good, direction. So why do we still have acceleration? Okay. Why? All right, because the direction of the velocity is changing constantly. Okay? The direction of the velocity is changing. Even though the velocity value itself, the magnitude of its velocity is not changing, its direction is changing. And so therefore you have acceleration. Why? Because how do we define acceleration? It's the rate of changing, it's the rate of changing velocity, right? And velocity by definition is what? The rate of changing position or displacement. And displacement deals with direction. Okay, so say here again, terminology and understanding the concept that we're talking about is important to remember. Because even though the value is the same, the direction is changing. And it produces acceleration. Okay? And you all know it works because, like I said, I've demonstrated. You probably as a kid would take something and swing it. Okay? You could feel that little tug on your hand. You had to pull back. Okay? All right? Okay. So we have uniform circular motion. So notice they talk about the components here. Now in reality, if you think about it, you have an X component when it's here, but when it gets over here, you got to realize that, well, actually at that angle, let me do this. If you were here, okay, and the ball is here, then you've got what? You've got X component, don't you, of velocity. But as it comes on around in its arc, notice when you get here, you have what? You not only have, you don't have quite as much X, but you have a whole lot more Y. Okay? And so to counter that, you have what? You have your acceleration has to counter that. The acceleration vector has to do what? It has to pull in the opposite direction, doesn't it? To produce your resultant. Okay? To get this curved path. To get the path to curve. So your acceleration vector has to be what? In the opposite direction. Okay? To keep it on that curved path. Okay? All right, so by definition then, when we look at uniform circular motion and centripetal acceleration, if we take the rate of changing velocity, it's velocity 1, notice they compare something, they throw something else in here, that delta S is the arc length, okay? The arc length. So if we rearrange the equation, the rate of changing velocity, or the change in velocity, is equal to what? The initial velocity divided by the radius r. Because why radius r? Well, we're going in a circle. Okay? We're traveling through an arc length, okay? All right, but you got to realize something, that even though the velocity vector is in this direction and it's related to the radius r, what happens along the path? Notice that the path is curved. Okay? It doesn't go in a straight line. It's a curved path. Velocity vector's here, but the path is here. Okay? You follow me? Velocity vector's this way, but the path is this way. Now that's a short time interval. So if we come in here and we say, okay, well, how do we find the velocity along that path? Well, how do you find it? Well, if you take the derivative of delta S, we could say x, even though it's a short amount, short value, very small value, with respect to time, what do we get? We get velocity. And so, and that's what this is telling you right here. We're taking the derivative of delta S with respect to time, and S is the arc length, okay? Then we wind up with what? We got velocity over r times velocity, or we get what? Velocity squared over radii. And that's how we derive centripetal acceleration, okay? Because you do have those two components, and basically what it is, it's you've got two components of velocity. You not only have velocity along the straight line path, but you've also got the velocity of the particle moving through the arc length. And that's why it's velocity squared. Okay, I hope that makes sense. Okay, it's a little bit ambiguous, but anyway, okay? And so that, now notice that's radial acceleration, okay? So what is radial acceleration? Well, that is the acceleration along the what? The radius. And so, what does centripetal mean, okay? Okay, well, we call this radial acceleration, but we can also call it centripetal acceleration. It is what? Center seeking. Centripetal means center seeking, okay? And if you come up here and do this demonstration yourself, you will feel the tug of the string on your hand. Well, the ball's out here, but how's it tugging here? Because the acceleration is towards the center. That's what, if you think about it, how do race cars on these huge tracks at Talladega, for example, how they're all running about the same speed? You know, when you got the sucker in the intake and everybody's got it in intake, how do you get ahead of somebody if you're all running 200 miles an hour? Well, you hit that bank curve. You know how to manipulate the curves. I mean, y'all have watched racing probably. The good drivers know how to manipulate the curves. Okay? And they know physics. When I hit this curve, I'm going to accelerate. Even though my velocity may be maxed, I'm going to accelerate based on where I am on that bank curve. And that's why, you know, NASCAR drivers, it's hard. You know, it's when you got, what, 50 cars out there? How many cars are in a NASCAR race? 50? It's a bunch, isn't it? I mean, and they're all bucking for that perfect spot. And so you're constantly moving. You know, it's 500 laps. So, I mean, you know. But again, you have to learn how to manipulate the physics, okay? A guy I used to work with said he went to Talladega and paid to ride, you know, and go down there and ride in a NASCAR, one of the drivers. I think they run about 150, 160, he said. And he thought, man, I thought this was going to be cool. He said, because I love NASCAR. He said, I got in that car, oh my Lord. And he said, I was doing pretty good till we hit the bank. And he said, when we hit the bank, we was running probably about 150, 160. And he said, I thought I was going to die. He said, literally, he said, I really thought I was going to die in that car. And he said, man, I went to screaming, get me out of here, stop this thing, get me out of here. And I think he only went one lap. I don't know how many laps they'd tell you. He said, stop, I don't need no more. And he told me the reason why. He said, when he hit that bank, okay, y'all, what's going on? What we just, uniform circular motion. All right, when you hit that curve, you go from a straight line. You got to remember inertia kicks in too. Because what does that car want to keep doing? It wants to keep going straight. That's why they run off. That's why it's so banked. Because if it's not banked like that, if it's like this, 150, 60 miles an hour, I don't care how good a driver you are, you're going straight. You're going to have a fence post somewhere you don't want it, okay? You're going to straighten that curve out, right? You are. So they bank it. What is it, 7-degree bank? Is it 7 degrees at Talladega? You can't walk up it. It's steep, okay. Yeah, well, I mean, let's according, you can look at it 70 or 7, according to which way you want to orient the axis, yeah. It's really steep, okay? He said when they hit that bank, he said all my blood went right here. He said it went to my rear end. And he said, literally, I thought I was going to pass out. He said, I mean, it just like that. And when we hit that bank, he said, you could feel it pull you down in that seat. And he said, I'm not kidding, I thought I was going to pass out. And so you think about it. Have you ever noticed how those guys, they're not kind of like me, a little Humpty Dumpty. No, they're fit, okay? They're, you know, if you think you have to tense your body up, because if you don't, your blood will, it's just like an airplane pilot. When they pull 6 Gs in a curve, why do you think that suit they wear blows up? They have a computer hooked to a compressor, and when they hit a real sharp bank, a jet pilot, the suit, real quick, blows air and compresses their body to keep the blood in the top of their head, because if they didn't, guess what happens when they hit that sharp curve chasing a commie pilot? You know, you can tell I'm an 80s kid, all right? And, yeah, boy, it was a communist when I was growing up, all right? Soviet Union's a big enemy, okay? But if you didn't, he'd pass out and, you know, okay, bye-bye. They might come back too. So, same thing on that curve. Those NASCAR drivers have to tense their body. Can you imagine doing that every time you hit a curve? I mean, you really have to be fit. You have to be physically fit to drive those cars. It's 500 laps and there's 2 curves, so that's 1,000 curves. And how long they last? 2 hours, 3 hours? How long's a race usually? You can tell I don't watch NASCAR. 2 hours? Yeah, 2, 3. So can you imagine just doing that almost nonstop? And when they pull in the pits, they're not stopped, what, 10 seconds? Not even that long, probably. And they're gone. So it's not like to get out and take a breather. Let me get my blood back in my head. And he told me, he said, it was freaky. He said, I swore I'd never get in one again. And he loves NASCAR. He loved it. He said, won't give me in one. So centripetal acceleration, okay? The blood was going in the opposite direction, wasn't it? Okay? All right, that makes sense. Okay, I hope. All right, so again, centripetal acceleration then is what? Center seeking, center seeking. Now there's another way we can solve this. Now I hope you wrote that equation down. That's an equation. That's uniform circular motion or centripetal or radial acceleration. Write that down for your formula. Oh, by the way, the units are going to be what? Meters per second squared, because it's acceleration. So that's the units. That's not going to change. Acceleration is acceleration, y'all. Okay? So center seeking. Now there's another way we can solve this. Okay? Notice we're moving through an arc. And by the way, if you go in a complete circle, that is the what? The outer rim of that complete circle is called the what? Circumference. And how do we find circumference? Huh? Yeah. So we can use it what? Pi r squared or 2 pi r. So the circumference of a circle is 2 pi r. Well, if you divide that by the time, guess what you get? You get velocity. Look, y'all, delta x over change in time. And really, I could probably leave the delta off on the t just to get technical. I mean, well, I say I could. Well, what if you started at time 3 seconds and went to 6 seconds? Well, it'd be 6 minus 3. Okay. Remember, time always has to be positive. All right. Okay? So look, all right, well look, if you go to this equation, look right here, and come in here and square that, looky here, you get that equation. Beautiful. So if we don't know the velocity, we don't have to know the velocity to find the acceleration. If we know the radius of the circle, all that right there, all those are constants. So if we know the radius of the circle and we know the time interval that it's going in one complete circle, the period, remember, how do we define period? Period and frequency are not the same thing. They are opposite. They're inverse of each other. The period is the time it takes to complete one cycle, one circle. The frequency, okay, are the cycles that occur in a time interval. Okay, does that make sense? In other words, how many times do you go around in 1 second? Okay? Or minute. Revolutions per minute. Okay? That's actually the frequency that the engine's running at. How do you think a mechanic, he's really looking at the frequency of the engine. The old way of doing it, the old timing lights, you know, they had a mark on the timing pulley and the block. There's a mark there and a mark on the pulley. They hook their timing light up to their plug wires, and if it's in time, you should be able to see the marks line up on every doot, 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 doot. They should line up. If it's out of time, then you're going to be able to see that they're not lining up. Okay? All right, revolutions per minute is frequency. It's the frequency of the engine they look at. Okay? And guess what? Frequency is sound. Have you ever had a mechanic, and these are good ones, man, they walk up, you got a rod knocking, or you got a lifter, bad lifter. They're listening to the sound of the motor. And those old mechanics, man, they could nail it. You know, you could never trick them on selling them a bad car. I mean, they could listen to one and say, no, that's a lifter knock. No, that's a rod knock. Why? It's a frequency different. Different frequency, different pitch. Okay? Okay? So revolutions per minute is frequency. It's not period. All right? Please don't confuse the two. So there's another nice little equation. Matter of fact, I kind of like using that one better than the other one. But we can use both of them, okay? It's a good equation, all right? All right, now, what about, and again, uniform circular motion? What does it mean, uniform? That means that the velocity is constant, but the direction is changing, all right? Projectile motion is uniform, okay, if there's no resistance. But now, what about non-uniform circular motion, okay? Non-uniform circular motion is when we have what? When the velocity changes through the path of motion, okay, the motion path. In other words, you don't have constant velocity, okay? It's not the direction that's changing, but it's the velocity. In other words, notice they use instantaneous, and they say it is instantaneous to the the acceleration component is parallel to the instantaneous velocity. So in other words, what are they saying? They're saying the velocity at this instant right here is also parallel to the tangential acceleration. Now, tangential acceleration can be, and if it's non-uniform, will be different than your radial acceleration. Okay? Why? Because it's fluctuating. It may speed up in its path. It may be speeding up right here on the bottom part of the path, but as it gets up here, gravity might slow it down a little bit. Okay? And so at this instant, the velocity may be a little bit less than it is at this instant. And so we have to take into consideration that the motion is not uniform. It's close maybe, but not quite. Okay? And so we look at what's called tangential acceleration. Do I need to even explain tangential? I mean, come on, y'all know what tangent is. Okay? You know what tangent is. We're talking about at this point, we're talking about right there. At this point, it's going to be right here. Well, I'm not drawing the arrows, but we're just following the arrows. At this point, it's going to be right here. It's tangent to the point. Okay? You know that. Okay? But we find it with the same equation, except we put tangential on it. Okay? All right, now what about relative velocity? Okay, relative velocity is, the key word there is relative to the observer. In other words, just because it may appear, let me ask you this, if you're out on the Great Plains chasing tornadoes, and a tornado's coming directly at you, what velocity will it have relative to you? Have you not ever heard the meteorologists say if you're out on the road somewhere and you see a tornado and you stop the car and it appears not to be moving, it is headed right for you. Now, the old-time meteorologists used to tell you that because of safety. You know, sometimes people get caught out on the road just unaware. They may not have the radio on, or maybe back in the day when the technology wasn't near what it is now, you know, tornadoes can pop up just, 5 minutes. You can go from a clear sky and bam, you got a tornado. And that really has happened, y'all. That's happened here in this area, in Alabama. 2 minutes, 3 minutes after clear sky, they have a major tornado. So that tells you how severe weather can get just before you blink. So back in the old days, they didn't have the technology, didn't have radios, didn't even mention tornadoes on the radio. It wasn't until the 1950s that they actually started issuing tornado warnings and tornado watches. Why? Because they didn't want panic in the public. If they come on the radio and says, we got a tornado, people will just go crazy. Okay? Panic in the public. All right. But still, there's part of me that thinks, you know what, you still need to warn people, And I realize broadcasts go out over a large area and tornadoes are specific. Okay? If there's a tornado in Boaz, it's not hitting Aberville. Okay? It's hitting Boaz. So I understand people in Aberville hear tornado and they think, oh my God. No, it's hitting Boaz. All right? Or vice versa. Selectively? Yeah. Uh-huh. Yeah. And that's the way it needs to be. Yeah. It's come a long, long way. I remember years ago when we didn't even have any tornado sirens hardly. You know where the tornado sirens were? Downtown. Yeah. At the fire department.
5 years ago when I started, 10 years ago when I started working on them, that's part of what I did with the county. So,
oh, yeah? Oh, neat.
We could only set them off like large numbers in certain areas.
Yeah.
We set off like 8 or 10 at a time.
Uh-huh.
Now we've got it, I can set them off on my cell phone.
Wow, neat. Per siren, yeah, that's the way it should be, But again, technology had to come along to catch up with it. So, but yeah, I remember when I was a kid, if there was a tornado warning in Marshall County, it was the whole county. It was the whole county, and the siren was only in downtown. Well, what if you lived out at Beulah like I do? Well, I guess you just got blown away if it's coming your way. Because we can't hear it in Boaz or Aberville. Well, that's according to which way is the wind blowing. All right. Now we have one at the fire department in Beulah, and that thing's even hard to hear sometimes. So.
They know the range on them.
Uh-huh.
And there's certain areas that we told them, we have.
Uh-huh.
If you look at them from the air.
Uh-huh.
Sometimes they might not be but a mile or two apart.
Yeah.
But you might not hear it from that mile.
Yeah, because of the terrain. Yeah.
On the mountain,
yeah.
You can hear 10 miles.
Yeah. 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 Terrain makes a big difference.
Yeah.
And what's on the terrain too. If you got a lot of trees, that'll catch a lot of that sound. I think that's part of what our problem is. So, said all that, say this, tornado's coming straight at you, you better get out and get in a ditch. You better get. You better, because it's coming, but it has a relative velocity of 0. Now, wait a minute, good and stinking well, it's moving, because if the tornado's here and you're here and it's moving this way, well, what about the dude that's over here? Well, look, he's going to see it doing what? He's going to see it moving that way, isn't he? Pretty quick. So he's okay, but you're dead meat. You don't take cover, okay? Well, the same. I'm trying to use tornadoes as a point to explain, okay? So it all depends on the frame of reference. It depends on the observer, what the observer's viewing, or maybe, and you can have more than one observer. You might have an observer here, and then you might have one, over here, okay? Well, the person over here looking at the tornado, the person over here, it's not going to appear to be moving as fast as the person over here, okay? All right, so it all depends on where the observation is taking place. All right, so let's just do one for a practice, okay? And I sat in my office this morning and I just worked one up because I think it'd be the easiest way to do it, and then we're going to get into some problems. All right, discard, put some slides in here. All right, and I do want to try to look at some problems today, so I want to, we still got some time. All right, because I'm sure y'all got questions. All right, so let's just say we've got a swimmer, we got a river, and we got someone that's going to swim across the river, okay, and they're swimming like this, and there's their feet, and there's their body, okay, and let's say the velocity of the swimmer is what, 4 meters per second, and the water's running this way, and let's say the velocity of the water is 2 meters per second, okay, let's use nice round numbers. All right, now, and let's just say the width of the river, let's just say from here to here, is 250 meters, okay, from here to here, across the river. All right, now, y'all, you know good and well as I do, you know which way the swimmer's going to go. Is he going to go straight across that river? Or is he going to swim at an angle? He's going to swim this way, isn't he? That's going to be his actual path. So this is going to be our what? Velocity relative, isn't it? He's going to fly along the hypotenuse, right? Yeah, not fly, swim, excuse me. Okay? All right, so how then, now this is an easy one. Now y'all look, what if the angles were different? What if the angle of the swimmer was this way and the angle of the water was this way? Then we've got components, don't we? And we have to find the components of each vector and add them up, and then do the square root of the squares, right? So that's the only thing that would change. Because what is the y component of the swimmer going across this way? What is the y component going straight across, going that way? Is there any y component going that way? It's 0. All right, what is the x component of the water going straight down? Is there any x component if it's going straight down? 0. So we don't have to add up like terms and then do the square root of the squares. We just go straight to the square root of the squares, don't we? Because look, what is this? This is a right angle. Okay, it's a right angle. So the relative velocity then is what? Well, we do what? 4 meters per second squared plus what? 2 meters per second squared. And we get what? What did I get? Did I get 4.47? Does that sound right? Y'all double check my math. Because I was working this morning, I boo-booed, and I caught my boo-boo, thank God. And I had to go back and fix it. I got in a hurry. All right. Is that right? Square root of the squares? So the relative velocity then of the swimmer, now remember that's relative, okay? That's relative. Relative to what? His position and the direction of the flowing water, right? Okay? He was swimming at 4 meters per second. That was his actual speed. Okay? But if there was a person standing over here on the bank watching, then the relative velocity of the person watching would be 4.47 approximately meters per second. Okay? Does that make sense? Now let me ask you this. What would be the angle? What would be this angle relative to going straight across? All right, y'all, that does not ever change. All right, so it's got what? 2 over 4. Now watch. What do we get? We get 26.57. Now wait a minute, are we done? Because notice where he's swimming. All right, let's draw our x and y coordinates there. Uh-oh, we're below the x-axis. So we got to do what? Orient it counterclockwise. So we got to add 270. And what do we get? 296.57? Does that make sense? All right. I don't believe you, Miss Shields. I tell you what, you take a compass out and you watch somebody do that. If you're looking straight across the river and they're going that way, remember you orient counterclockwise from a positive x. Take your compass. Remember your compass is oriented north. You know, you got north. Let's see, where's north? North, east, south, west. And if you were looking at that individual swimming across, guess what? That compass needle's going to come all the way around and go 99, let's just say 299 degrees. Okay? All right? 296, excuse me. 296.57, 297. Close enough. Okay? All right? That's easy, wasn't it? So it's the relative velocity. And again, why do we say relative? Because it is to the observer. All right? Did not say actual. Relative. All right. And if you want a formula for relative velocity, it's this right here. It's the relative velocity is equal to, and we'll just use swimmer plus the velocity of the water. If you want to put A and B there, okay. A and B. All right. Okay. Now let me ask you this. How long would it take to swim? All right, so we found the relative velocity is what? 4.47 meters per second. We had the velocity of the swimmer was what? 4 meters per second. Velocity of the water was 2 meters per second. All right. Then how long? All right, remember, here we are going across the river. Okay. I didn't draw my waves. Okay, so he's here and he's swimming, the arm there and the leg and whatever. Okay. All right. So how long? What would the time be? How long would it take him to cross the river? Okay. Remember now, he's swimming this way with what? 4 meters per second? And the distance from here to here is what? 250 meters, isn't it? All right, so what two parameters match up? Well, the velocity of the swimmer matches up with the width of the river, right? Delta X. If you want to put delta X, W for width. Okay. All right. So how long will it take him? You say, yeah, but Mr. Shields, he swam at an angle. Amen, brother, sister. But that does not change a cotton-picking thing because he's still swimming at 4 meters per second. All right? Yeah, he moved at an angle, but his velocity did not change. The relative velocity was different, but actual velocity is 4 meters per second. Okay, y'all, how do we find it? Remember this? Yeah. Remember this formula right here? It's 9th grade physical science formula. And again, delta T, we're going to subtract from 0. Time minus 0, okay, is time. All right. So we solve for T, don't we? So we solve, and I'll just do this. We're going to say time is equal to what? The change in displacement, which was 250, divided by what? The average velocity. And we're just assuming it's average. Okay, I didn't tell you it was, but we're going to go ahead and assume it. And so we got what? 250 meters is equal to what? What was it, 4 meters per second? And so we get a time of what? 62.5 seconds? Is that correct? Is that correct? Okay. Now there's something else missing. How long, how far downstream did he swim? I'm going to do this now. We're going to say delta X. We used a W. We're going to use a D, downstream. Question mark. All right, let me ask you something. He did swim at an angle, but the time it took him to get over to here is the same time it's going to take him to get down to here, right? It has to be. Okay? Time's not going to be different this direction. Okay? It can't be. All right. Well, you remember how to find delta X? Well, delta X downstream is equal to what? Well, take your equation and solve for it. Velocity average times what? The time, right? Now, wait a minute. What average do we use? Well, if you remember, the velocity of the water was what? 2 meters per second. Is that right? Are you with me? That's downstream. And so we got what? 2 meters per second times what? 62.5? Does that make sense? And so we get a delta X. The change in displacement downstream is what? 125 meters. Right? Can you do that? Might be a good test question. Can we do that? I may put one on. You know, I can't put them all on there. I haven't in times, well, I say I haven't. A couple of years ago I think I did, but last year I don't think I did. I have to go back and look at the test. But I could on this one. Because, y'all, really, that's easy. That's just Pythagoras. That's all it is, Pythagorean theorem. And then come back to this little equation right here, and you just solve for your missing components. Okay? And you know you got to have 2 of the 3 to solve it. You got to. You got to have 2 of the 3 variables to solve it. All right? Unless it's a simultaneous equation, and we're not to that yet. Okay? We will, though. All right? When we get into forces and stuff. Okay. All right? Okay. Any questions on that? All right. Now, what about this? What if we had this situation, same situation, same person. We got the width of the river. It's 250 meters. We know that the water, but now wait a minute. How would at what angle would the swimmer have to swim at upstream to go straight across the river? All right. Well, we know that the river is flowing that way. We know, now this is the velocity of the swimmer. This is the velocity of the water. That has not changed, okay? So we got what? 4 meters per second? Yeah. What's the velocity of the water? 2 meters per second. Now we want to find that angle right there, theta. What is that going to be? At what angle would they need to swim upstream to go straight across the river? Huh? So, what angle is needed to swim upstream so that the swimmer goes straight across? What angle? Well, let's see. We got opposite over hypotenuse. What is that? Sine, isn't it? Sine theta. So we do arc sine, don't we? And we get what? 2 over 4. And what do we get? 30 degrees. Now, is that oriented correctly with the positive x-axis? Well, where's my axis? Right there. Right there's my axis. So he's got to, how would we write that? What would you say swim at an angle 30 degrees upstream, right? Or 30 degrees north of east. Does that make sense? Yeah. That's easy, wasn't it? That's just plain old trig. All right? Okay. All right, now, so if this is the velocity of the swimmer and that's the velocity of the water, what is the relative velocity? Because, gummit. Sorry. All right. Okay, relative velocity, question mark. That is this velocity going right across here. Because remember, the person watching this over there on the bank, remember now, the swimmer's swimming at an angle. Have you ever tried to swim upstream? Anybody ever been on the Akoi and fall out of a raft on the Akoi? Boy, you better pray to God you're not in a rapid, right? What do they tell you if you fall out? Swim what? Swim down, put your feet up, that's right. And they always kind of tell you to do what? Swim across. If you can, swim at an angle against the current, so you'll go straight across, right? But typically you just try to swim straight across and you'll eventually hit the bank as you're going down, right? I've had that happen. It was at flood stage. I'm talking, you know how the water runs over that spillway? Now I'm talking about on the lower Akoi. This is before they even had the upper Akoi. We used to, it was just from the spillway all the way down to the bridge was lower Akoi, and that's all you had to raft. Now they got 2. Okay, so I'm dating myself here. All right. And you know how the water's usually coming over that spillway about that high? We were on it, and I am not lying. It was coming over that spillway probably about, the put-in area looked like Gunnersville Dam when they have the turbines all going. And we were gung-ho. And we didn't get from here to those cabinets, and me and my dad and my nephew fell out. We just hit a real bad, turbulence, and it just, my weight, I just didn't shift my weight quick enough, and me and my dad, I knocked my dad out, my nephew went out, and he was little. That was scary. That was scary. Okay. So to people observing, they said, look at those idiots. But needless to say, and my brother says, hang on to the paddle now. If you fall out, don't lose it. Well, my brother's older, so I honor my older sibling. And so I was doing this. I was holding and swimming with one arm. And I told him when I got out, I said, I ought to break this thing over your head. Because I still had it in my hand. I didn't let it go. I said, you better bronze this sucker because I nearly drowned. And so I learned. I told him, I said, bro, I love you. I'll buy you another oar if we can lose it. But I said, I am not hanging on that thing. Because I went probably 200 yards down the river for you. You know, it's a long ways till you hit the first calm spot. And it was rough. I bet I drank 2 gallons of water. I am not kidding. I am not kidding because, you know, I had my feet up and I swim in one arm and water hit me in the face. And, you know, you take a breath and water hits you in the face and you'd swallow, you know, a bunch. And I was so give out when I got to that first calm spot, and there was some rafters right there, and I was screaming at them, throw me a rope. I couldn't swim no more. I was give out. So, but anyway, my brother finally come and picked me up. But I told him, I said, when I fell out, I said, get Dad and get my nephew out. He was about 7 or 8 years old, 9 maybe. He was too young probably to be in the raft. There were several adults, but we had too many kids in the raft. So we learned from that experience, okay? So I know about swimming across rivers, all right? And so we want to find a relative velocity, okay? Well, how do we do that? Well, look, y'all, still Pythagorean. Watch now. It's still this right here. It's the velocity of the swimmer plus the velocity of the water. But now, wait a minute. Which part is which? This is a squared plus b squared is equal to c squared, isn't it? Well, now we've got c squared, and we've got what? B squared. We want to find a squared, don't we? So how are we going to need to find the velocity of the swimmer? Are you with me? See, look at your triangle. The hypotenuse is C, right? The base is what? B, or the short side's B and the long side's A. Now we've got to find A. Okay? So A then is equal to what? Well, it's going to be the velocity of the swimmer minus the velocity of the water. And of course we know it's Pythagorean, so let's plug it in. So the relative velocity is equal to what? So we got what? 4 meters per second squared minus 2 meters per second squared. And you should get a relative velocity of 3.46, right? Everybody do that? Yeah. Okay. Now notice the huge difference in velocities there, relative velocities. One's going up the river, one's going down the river. Does that make physical sense? Are you going to, look, even though you may be swimming at the same rate, the person watching you is it's going to appear to them you are moving what? Going upstream, you're going to appear to me moving slower than going downstream with the water. Think back to the other problem. He was swimming across at 4, but relative, he was 4 point what? 4.7, something like that. So he was moving faster than he actually was. Appears, relative, okay? So does that make sense? Okay, now what about the time interval? Does that affect the time interval? Okay, remember now, what components match up? Now relative velocity matches up with moving across the river. So what will that equal? Well, T is equal to what? 250 meters divided by what? The relative velocity is 3.46. Remember, you got to match up. You got to match up what goes with what. Look, 250 goes with relative velocity now. Doesn't go with the velocity of the swimmer. Swimmer's swimming at an angle. You follow me? And so what do we get? And by the way, that's meters per second. We get what? 72.3 seconds? Wow. What was the other time? 62.5? So is it going to be a longer swim? Sure it is. Does that make physical sense? Well, sure it does. Because you're going against the current instead of with the current. If you've ever been in a river, Hiwassee, Nantahala, Ocoee, what's that river up at Helen, Georgia that you always see people posting pictures of them riding in the raft? Yeah, that one. I can't remember the name of it. Is it the Nantahala? No, Nantahala's in North Carolina. Okay. The what? It might be. Up in Helen, Georgia, northeast Georgia. It might be. I can't remember for sure. Okay? All right. Okay, so hopefully now you understand what relative velocity is and how to calculate it, okay? All right. I want to stop video and start another one.